Okay, Chapter 5, Section 1, Antiderivatives and Indefinite Integrals. Okay, so in math, whenever you learn how to do something, you also think about how to undo it. So for instance, we learned how to add, right? So you learn how to do something like 3 plus 2, we know addition. And then soon after, we came and learned how to undo it. So we learned subtraction. 5 minus 3 equals to 2, right? So the operations of addition and subtraction are inverses of each other. They undo each other. You can add something, you can take something away. Later, we learn how to multiply. So we learn how to do 3 times 2 equals to 6, right? Multiplication, and then soon after we learn how to divide, right? So 6 divided by 3 equals to 2. Okay, well, in the same spirit, so far we've learned a whole lot about derivatives, right? So we've learned how to take the derivative with respect to x of, say, a polynomial function, x cubed plus 2x to the power of 4. We know that this is equal to 3x squared plus 8x cubed, for instance. So now that we've taken the derivative, we want to learn how to go backwards. How do we undo this process? So we're going to start off with something that looks like this. So given 3x squared plus 8x cubed, we want to be able to go backwards so that our answer will be something that fits this form, right? So how to undo the derivative. We also learn how to take the derivative of other functions. So for example, we've worked with logs. And we know that the derivative of a log is just going to be equal to 1 over x. So again, we're going to start off with this. Given the 1 over x, we want to be able to go backwards so that our answer will be ln of x, right? So we want to be able to undo the derivative, going backwards. That's what an antiderivative is. Let f of x equal to x to the third power. Let's say that this is the result of a derivative. What kind of a function exists out there such that when we take the derivative of that function, this is our answer, right? That's what we want to figure out. So we want to find capital F of x such that when we take the derivative with respect to x of this function, capital F of x, that the answer is going to be equal to lowercase f of x, right? So we want to figure out a function such that its derivative with respect to x of capital F of x is going to be equal to x to the power of 3. Okay, well, we know that when we take derivatives, so recall that the pattern that we've established for taking derivatives is as follows. If we have the derivative with respect to x of, say, x to the 5th power, we know that taking the derivative, the process is to bring that 5 down below to the side, making it a factor, and then multiplying this to the power of 5 minus 1, right? So we subtract 1 from the exponent. That's when we're taking derivatives. So if we want to go backwards, we know that it's going to have to be something that will undo this little process of subtracting 1. We're going to have to add 1. So whatever this is, it will have to be something of the power 4. Like that, right? So that when I take the derivative, I bring this 4 out in front, and then I subtract 1. So this is kind of a guess and check process here. We're going to just try different things. I know it has something to do with x to the 4th, but now, when I think about what that is, or what the derivative of this is, so now, let's put this over here, the derivative with respect to x of x to the 4th, I know that that's equal to 4x to the 3rd power. So I'm getting close. I do have the correct power, but there's a 4 there, and I don't necessarily want that 4 to be there. So I can undo it by multiplying this by 1/4. Okay, so we're going to let capital F of x equal to 1/4 times x to the 4th power, or also known as x to the 4th power divided by 4. Right? So it's sort of a guess and check process. You're going to kind of think about your derivatives. You're going to rely a lot on the derivatives. You got to think of a function whose derivative will give you the result you're looking for, and then play with it a little bit and figure out if it works or not, and then make adjustments to it. So now, we can check it to make sure. Let's see, check. The derivative with respect to x of capital F of x, well, if this is the defined value, then this is going to be the same thing as the derivative with respect to x of 1/4 x to the 4th, and we know that that's going to be 1/4 times 4 x to the 4 minus 1, and now the 4 and the 1/4 cancel. That was the reason why I put a 4th there, and so this gives me exactly what I wanted, x to the power of 3. So we've done it. We figured out a function such that the derivative of that function equals x to the 3rd power. So we say that capital F of x is an antiderivative of lowercase f of x. So thus, capital F of x equal to 1/4 x to the 4th is an antiderivative of lowercase f of x, which is equal to x cubed. Okay, notice that I wrote an antiderivative because it's not necessarily the only one. Consider what happens if I let capital F of x equal to 1/4 x to the 4th plus 1, right? I can just put an extra constant there, and notice that if I take the derivative with respect to x of capital F of x, I still end up getting the same result. I get 1/4 times 4 x to the 3rd power, and then the derivative with respect to x of 1 is 0, so we just get a plus 0 there. Erase this. We just get a plus 0 there, so the derivative with respect to x of this function, f of x, is still equal to just x to the 3rd power. So here, maybe I should have labeled it a little bit different. Let's call this capital F hat, capital F hat, capital F hat. So it's a little bit different than that one. So what we have is two different functions that work. This one works. This is a function such that when I take the derivative of this function, it gives me x cubed. And so is this one. Right? In fact, you can always just put a constant at the end here, because when you take the derivative of a constant, you get a 0. So we can easily come up with a whole family of functions that will all work. So f of x equal to 1/4 x to the 4th power plus 1 will work. Let's call that f sub 1. F sub 2, another one that will work, will be 1/4 x to the 4th plus e squared. Remember, e squared is just some constant. It's not a variable. And the derivative of that will still be 0. Another one that will work, f sub 3, well, that would be 1/4 x to the 4th. It could also be a minus, right? Minus pi to the power of 3, pi cubed. Again, the derivative of this is just going to be 0, so it still works, right? So for all of these, doesn't matter which one you choose, the derivative of each of those is x cubed, right? So in any one of these cases, we could say that any one of these is an antiderivative of x cubed. In general, then we could say that f sub n, doesn't matter, some general function, x to the 4th power, is equal to this plus some constant. Oh, you know what, let's get rid of this little n there. just this one has 1, 2, 3, whatever. So then just in general, we can say that capital F of x equals to 1/4 times x to the fourth plus c, where c is any real number, where c equals any real number. And so there's a whole family, an infinite number of functions out there that will all be antiderivatives of the function x to the third power. So a function f is an antiderivative of a function lowercase f if capital F prime of x equals to f of x, right? That's what we've been saying. The antiderivative of a function f, this looks a little messy here, but the antiderivative of a given function lowercase f is going to be a new function, capital F, such that when you take the derivative of capital F, it gives you the lowercase f function. Right? So like in our little example, if we're asked to find the antiderivative of this function, lowercase f equals to x cubed, then the antiderivative is going to be a new function, capital F, such that the derivative of that function equals to the given lowercase f function. Okay, so for this particular case, capital F ends up being 1/4 x to the fourth plus some constant c, where c is any real number. And the proof is that the derivative of this function equals to exactly what we wanted, x cubed. Okay, so because c is allowed to be any real number, then antidifferentiation doesn't give you a unique answer. It gives you a whole family of functions, a whole family of answers. Sometimes you get to pick what that constant is if they ask you, if they force you to pick one in particular. And obviously a very common answer would be for people to pick 0, right? The most common answer, or maybe a 1, another very popular answer. But sometimes there might be a very specific antiderivative that you're looking for, and they might give you some information to be able to identify which one it is. And sometimes you'll just be asked to identify that there's a whole family of answers by leaving your results with a plus c at the end. Okay, theorem 1, antiderivatives. If the derivatives of two functions are equal on an open interval, a to b, then the functions differ by at most a constant. Symbolically, if capital F and capital G are differentiable functions on the interval from a to b, and f prime of x equals g prime of x for all x in a and b, then f of x and g of x are equal to each other, and they're off by some constant at most, right? And of course that constant could be 0. Okay, example 1, note that the derivative of the function x squared over 2 is equal to x, right? Let's confirm that on the side here. So if we have d dx of 1/2 x to the second power, we know that this is equal to 1/2 times 2 x to the 2 minus 1 power. The 2's cancel, giving me x to the first power. So this is true, right? So x squared over 2, the derivative of that equals to x. So part A, find all antiderivatives of the function f of x equals to x. Well, this is kind of a spoiler here. It's giving it to you right there, right? So for part A, find the antiderivative of f of x. When you see that word, find the antiderivative, right? What is that? We need to find a function whose derivative equals this. That's what we want. And well, it's, spoiler alert right there. So capital F of x equals to x squared over 2. All right, so just as we established there, this is a function such that its derivative equals to f of x, right? So note that f prime of x, first derivative, is the same thing as the derivative with respect to x of the capital f of x function, just different styles of notation. They both mean the same thing, and both of them equal to exactly what we're interested in this. So we've established that this is equal to f of x, right? We've established that capital F prime of x equals to f of x. However, it doesn't say just find an antiderivative, it says find all antiderivatives. So that's when we have to recognize that there is an infinite number of possible answers. So we put plus c, where c is any real number, where c equals any real number. Right? We can put x squared over 2 plus 1, x squared over 2 plus e, x squared over 2 plus pi. It doesn't matter. As long as this is some constant, we will have a function such that its derivative is equal to x. Okay, so that's the answer to part A. Find all antiderivatives. That's this guy. Part B, graph the antiderivatives of f that contain the point 0, 0, the point 0, 1, and the point 0, 2. Okay, so for part B, we're given some additional information that can help us find the value of c. So an additional constraint. So for part B, let's start off with the 0, 0. B. So graph the antiderivative. So we're going to be graphing this newfound capital F. We're not graphing lowercase f, we're graphing capital F. Okay, so it's going to be capital F of x equals to, I'll write it this way, 1/2 x squared plus c. And when we know that 0, 0 is also a point, that means that 0 is a chosen input value and 0 is the resulting output value. So from here, we can conclude that it must be true that 0 equals to 1/2 0 squared plus c, right? Where this 0 is the output. That one went there. Oh, put it this way. This is the output that went there, where this is the input that goes there. Good. And well, in this case, we're going to get that 0 equals to c, and so capital F of x then becomes 1/2 x squared plus 0. Okay. Sometimes 0 is so easy that it gets a little confusing. Let's try another one. The other one that they gave us was 0, 1. So now, if we have the general formula for the antiderivatives, and now we're looking at 0, 1, that means the output is 1, 1, when the input was 0. Okay, so then this still becomes 0, so we get 1 equals to c. So now our function becomes 1/2 x squared plus 1. Good. Okay, last one. 0, 2. Okay, well, we see a pattern here. Hopefully this won't be hard. Capital F of x equals to 1/2 x squared plus c. So if we're also including the point 0, 2, it means that 2 is the output when 0 is the input. So again, this just means that c equals to 2. And so we have capital F of x equals to 1/2 x squared plus 2. Okay, all of these are parabolas. And then the 1/2 out in front affects how wide they open, right? So it opens a little wider than the standard parabola. And this one goes through the origin, this one goes to the point 0, 1, and this one goes to the point 0, 2. Okay, so let's use Desmos to graph these. Okay, so here are our graphs. They're all parabolas. They open up, they're concave up, and they are, there's a family of functions here. So one of them goes through the origin, that's the purple one here, plus 0. One of them goes through the point 0, 1, that's this one. And then another one goes to the point 0, 2. Okay. So they're all the same type of graph. They've just been shifted up and down by some constant. So in general, let's do this, plus c, where c gets to be any value. Let's put it in red. So depending on the value of c, we can see what's going to happen to the shape of our graph. It just shifts up and down depending on the value of c. C could be any constant at all. And so we keep the same shape. It just scrolls up and down in our graph. Okay, and that also kind of answers part C over here. How are the graphs of these three antiderivatives related? Well, as you can see, they're the same graph. They've just been shifted up and down depending on that constant value C. Okay, indefinite integrals, formulas and properties. So the symbol, this little elongated symbol here, the symbol integral of f of x dx, this notation here, the indefinite integral is used to represent the family of all antiderivatives of f of x. And we write that the integral of f of x dx is equal to capital F of x plus some constant c if it's true that the derivative of capital F of x equals to lowercase f of x. Okay, so the symbol, this little symbol, it's like an elongated s, the symbol is called the integral sign. So this is the integral sign. And the function f of x is called the integrand. So that's the function that you're integrating with respect to d of x. The symbol d of x indicates that the antidifferentiation is performed with respect to the variable x. The arbitrary constant c is called the constant of integration. Okay, that's this guy here. So putting things into this format of notation, earlier we were working with this one. We had f of x was equal to x cubed. And we found that there's a whole family of functions that look like this. 1/4 x to the 4th power plus c. And so putting it into this style of notation, we'd say that the integral of f of x dx is equal to capital F of x plus c, where in this particular situation, this would be the integral of x cubed dx is equal to 1/4 x to the 4th plus c, right? That's true. And then, of course, we've already confirmed that it's true that the derivative of this is equal to that. So this is pretty common as you work in this section. You always have to kind of think backwards. What kind of a function out there exists so that its derivative is equal to the integrand? Okay, so when this is given to you, this will be presented as a homework problem. Integrate x cubed dx. Okay, so you got to focus your attention on this. Confirm that these letters match, because this is letting you know what's the variable of integration and the variable of anti-integration. The variable of anti-differentiation. And so you have to think to yourself, back from chapter 3 when we worked with derivatives, what function out there exists such that when I take the derivative of that function, it gives you x cubed. Okay. Another example, very similar. How about if it was just x to the power of 2 dx, right? So this could be given to you. Given this, find the integral of x squared dx. So you got to think to yourself, what kind of a function exists out there such that its derivative is equal to this? So we know that when we take derivatives, we subtract one from the exponent. So I can guess that it has something to do with that, right? So kind of guessing and checking, I know that I would bring the 3 out in front and then subtract 1 to give me the correct power. But I don't necessarily want that 3, so I have to multiply this by 1/3 so that when I bring down the 3, they cancel and give me the result I want. And then, of course, there's a whole family of functions that will work, so we have to introduce or include that plus c. Good. And so that matches up with this right here. And we can check confirm that it's true that when we take the derivative of this function, 1/3 x to the third plus c, the answer really will be 1/3 times 3x to the second plus 0, and then the 1/3 and the 3 cancel, giving you just the x squared, which is exactly what we were interested in, just the x squared. Okay. So here's the exact same thing. We have the integral of x squared dx. We know that the anti-differentiation will give us to x cubed divided by 3 plus some constant. And that's because when we take the derivative of this, we get to the x squared. Okay, now notation, remember there's nothing special about the letter x, so we'd get the exact same answer if we shift it over to the letter t, for instance. The integral of t squared dt. So the only thing that's important to note is that these two letters match, right? We're taking the anti-differentiation, antiderivative with respect to t. Good, and then we get a very similar answer. Okay, nothing special about the letter x or t, so we can also use, say, the letter u, another very popular letter in calculus. So the integral of u squared du, the only thing that's important is that these two match, they must match, is going to be a very similar answer, u cubed over 3 plus some constant c. And again, we can confirm that this is true because when we take the derivative with respect to u of this function, we get exactly the integrand that we were interested in, u squared. Okay, so indefinite integration and differentiation are reverse operations of each other, except for the addition of constants of integration. Symbolically, this is expressed in the following way. Okay, so just think about, for example, when we wanted to, if we wanted to cube root x, and then we want to take that and raise it to the third power. Raising something to the third power and taking its cube root are opposite operations. They undo each other. This just ends up giving you x. Or if we take a number and multiply it by 3 times x, and then we also decide to divide it, the operation of multiplication and division undo each other. Either way, we get to x. And in the same spirit, that's what happens here. We have some function f of x, and we're integrating it. So we integrate it. But then we get an answer, and then we take that answer and we take its derivative. Well, these two operations undo each other, and we get back to where we started. Good, that's what this is saying. Likewise over here, and maybe it would be a little neater if it was this notation. Remember, f prime of x is the same thing as the integral of the derivative with respect to x of capital F of x dx. And so again, this integral sign and this differentiation sign undo each other. And so we end up with just capital F of x plus a constant. So that's the only thing that's a little bit different. We have to be careful about when you go in a certain direction, you have to be careful about the possibility of other functions that also solve your statement and are off by just a constant. Okay, so let's try and establish a pattern. Let's see, if we wanted to find the integral of x to the power of, let's just pick 5 for now. Let's figure out what that answer is. Something whose derivative gives you the x to the 5th. Hopefully we see that it has something to do with a 6 there. Because when I take the derivative of this function, I'm going to bring the 6 out in front and then subtract 1. Right? So then I don't want necessarily that 6, so we got to multiply this by 1/6. Always attach the constant, and let's check. Let's check to make sure it's true. So finding the antiderivative in this chapter, there's always a guess and check game, right? So guess what it is and kind of confirm that it works to make sure that you're actually getting the result we want, right? If it works, the answer should be x to the 5th power. Okay, so let's check it. The derivative with respect to x of 1/6 x to the 6th power plus some constant. Well, that's going to be equal to 1/6 times 6 x to the 5th plus 0. And then the 6 and the 1/6 cancel to give me exactly what I wanted, x to the power of 5. Good. All right, let's try the next one. Well, what if it was just the integral of x to the 6th dx? Well, okay, the pattern, hopefully it's starting to come into focus. This is going to be x to the 7th power. And then when we take the derivative of this, I know I'm going to have a times 7 here. So I need to multiply it by 1/7. And then there's a constant there. Okay, so just kind of guess and check your way through that, and then come over here and confirm that it actually works. So is it true that the derivative with respect to x of 1/7 x to the 7th plus c really does equal to x to the 6th power? So this will be 1/7 times 7 x to the 7 minus 1. And now the 7 and the 1/7 cancel to give me exactly what I was expecting, x to the 6th power. Okay, so we did a couple of these, and hopefully that's enough to see what the pattern is going to be. So in general, if I have this, x to the power of n dx, just like I've seen before, the pattern is going to be that the answer is going to be x to the power of n plus 1, right? 6, we always add 1 to get a 7 there. From the 5, we add 1 to get to the 6 there. And then whatever that is, we have to multiply it by 1 over n plus 1. And then add a constant. Good. So that's just the general pattern that we're going to run into whenever we see something of this form. Right? And math, we love patterns. We want to find all these patterns so we can box them up and have a form, a general format that people can follow. Notice, however, that we do have a problem in a particular case. Consider the situation where we have x to the power of -1 dx, and then we follow our little pattern. Okay, so that's going to be x to the power of n minus 1 plus 1, but then that becomes 0, right? So then this numerator then becomes 0, and then following the pattern, this would be 1 over minus 1 plus 1, which becomes 0. So the pattern, you're dividing by 0, so that's no good. And then anything raised to the power of 0 is going to be equal to 1, except maybe for the case where x equals to 0. So, what's the answer going to be to this one? This looks like the pattern says that it's this. Well, I don't know what that is, but it's undefined because of the 0 there. So the constant, the constant is not happy. And remember, this is just a guess and check process, right? So you're thinking, okay, well, I know, let's just get rid of that. But even if we get rid of this, this is still problematic. The derivative of this is not equal to that, right? So it all breaks down. Okay, so this rule almost always works, but it doesn't work for the case where n equals to -1. Right? So this is where n cannot be equal to -1. We'll figure that out separately. Remember that x to the -1 power, well, that's equal to 1 over x dx. Now, what kind of function out there do we know of such that the derivative of it equals to this? Right, so here, just to make sure it's clear, this is x to the -1 dx. This is equal to this. Okay, so if you recall, we're looking for a function whose derivative equals to 1 over x. And so hopefully ln of x comes to mind. So ln of x is a function whose derivative equals to this. But we do have to be careful, though, because remember that the domain of the ln function is positive numbers. I'll put it here. Domain of the ln function is positive numbers. but there's no guarantee that x is positive, right? It's not guaranteed here. X is free to be a variety of things. So we'll get into the limits of integration in a little bit, but there's no guarantees that this is positive. So we do have to adjust this a little bit and introduce or include an absolute value here. So it's absolute value of ln of x, and then of course we have a plus c. Okay. And then of course we can check that it's true. The derivative with respect to x of ln absolute value of x plus c is equal to 1 over x. Good. Okay, so we have two patterns now. Let's box this guy up. So we have this pattern here. When you see something that fits this form, this is a pattern we can use. When you see something that fits this form, this is a pattern we can use. We love patterns. So here's a couple more patterns that we get to use as well. Okay, formula. So indefinite integrals of basic functions. Okay, so here's one that we already looked at. So the integral of x to the nth power dx is equal to x to the n plus 1 divided by n plus 1 plus some constant. And this is valid for any value of n except n is not allowed to be equal to negative 1. We also looked at this one, the integral of x to the negative 1 dx, which is equivalent to the integral of 1 over x dx, is equivalent to ln absolute value of x plus c. Good. And also note that, I didn't point this out, x is not allowed to be 0, right? When we integrate this, of course, we have 1 over x, and, well, x is not allowed to be 0, otherwise we would be dividing by 0, so keep that in mind. And also we have this one. This one's an easy one. The derivative of e to the x is e to the x, so therefore the integral of e to the x is e to the x plus some constant. Okay, also we have that if we have the integral of k times f of x dx, then what we could do is pull that k out in front. As long as it's a constant, it's not a variable, it doesn't have anything to do with the variable of integration. Good. So this is saying that, for instance, if we have the integral of for instance, if we have the integral of 7x to the third power dx, well, that's just some constant. That's 7, right? That would be this k constant there. So according to this property, we know that we can just pull that on the outside and then deal with the rest of the integral, right? We can factor out a constant that's being multiplied. And then, well, we can just follow the rule from before. We know that this is just going to be equal to 7 times, and this is going to be 1/4 x to the 4 power, like this, plus some constant. Okay, so this is the result of finding the antiderivative of this. So that goes into that. So the whole thing gets multiplied by 7. So technically, this becomes 7 times 1/4 x to the 4th plus 7 times c, where c is some constant. So it's actually technically 7c, but this is some constant. Some constant times 7 is just some other constant. So very often, people just ignore that it's 7 times a constant and just say it's a constant. And there might be a little subscript to show that it's actually a little bit different now. It's 7 times some constant c. It's, it can't be the same value c, so you could put like a little not there, or a little 1, or a little 2, or you can also put like a little hat, something like that. But most of the time, people will just kind of ignore this step here and assume that it's kind of known. So when you look at the back of the book to find your answers, most of the time you'll just see plus c, even if they really do mean that there was some constant like a 7 that needed to be multiplied times this. So maybe putting a hat here and a little hat there just to show that it's different from that c, and then we get to our final answer. Okay, so that's what property 4 is letting us know. If we have a constant, we can pull it out. And finally, the last one we're going to look at right now is that if we have an addition or a subtraction of two functions in the integrand of an integral like this, then this property says that what we could do is separate them this way. So we can separate them into the addition or subtraction of two different integrals. So for example, if we were asked to define the integral of x cubed plus e to the x dx, right? So here we have the function f of x is this one. And here we have that the function g of x is this one. So instead of dealing with one big ugly equation like that, that's this, the sum of two functions, we can separate them. Property 5 says that we're allowed to separate this as the integral of x to the third dx plus the integral of e to the x dx. Okay, so that's always true whenever we have an addition or subtraction of two different functions. We can separate them. That's a very useful property. Okay, so we have 5 properties that we get to use to solve integrals. Obviously, we didn't prove any of these. So we just get to use them, apply them, love them. Don't worry about how to prove them yet. That's not really something that's in the scope of our class. Okay, so when you see something of the form x to the power of a number, right, make sure that you don't have it backwards. We have not yet discussed the opposite. So for example, we know how to solve this now, following this rule, but we still don't know how to solve this, right? So, we haven't gotten to that yet. So don't confuse them. This is where we have x to the power of some constant, and we want to integrate it. That's rule 1. Also, we have e to the x, right? Integral of e to the x, no problem. And then we also have integral of 1 over x is equal to ln of x. Again, also don't confuse the other direction. We know the integral of 1 over x dx. We got that one. But we don't know the integral of ln of x, right? I don't know that one yet. Right, so don't confuse them. Something whose derivative equals ln x. I don't know what function out there exists so that its derivative equals to ln of x. We haven't touched on that yet. Okay, so let's try some of these problems. Okay, so thinking of a function such that its derivative equals to 7, that would be 7x to the power of 1, right? Its derivative equals to 7, plus a constant. Good. This one, well, one of our properties says that we're allowed to pull the 4 out. So this is 4 integral of e to the t dt. And so we know that this is going to be 4 times e to the t plus some constant c. So again, just as we covered before, this could be some c hat. So then this is just 4e to the t plus c, where c equals to 4 times c hat. So again, most of the time people just kind of ignore this step here and just jump right to that. Okay, another one. Again, one of our properties says we can pull out the 3. So this is going to be equal to 3 integral of x to the 6 dx, which will be equal to, and I'm just going to skip that step there and say that it's 3 times, and this is going to be x to the 7th power times 1 over 7, taking the derivative of that, plus some c, right? So most of the time this is what people do instead of this little step here. Good. And then we can just simplify that as 3x to the 7th power divided by 7 plus some constant c. Okay, let's try another one. The integral of 2x to the 3rd minus 3x plus 4 dx. So again, one of our properties says that we have addition and subtraction. You can separate them. So this is equivalent to the integral of 2x to the 3rd power dx minus the integral of 3x dx plus the integral of 4 dx. Okay, so here we're able to pull out a constant 2, be 2 integral of x to the third dx minus, and here we can pull out this constant, be 3 integral of x dx plus, and then we'll leave this alone as a 4 dx. Good. Okay, so now we can find the integral of each one of these. So this would be 2 times, remember we subtract 1 to find derivatives, and we add 1 to the exponent to find antiderivatives. So this is going to be 1/4 x to the 4th power minus 3, and this is going to be 1/2 x to the 2nd power plus 4x, right? Okay, so then kind of guessing and checking through this, try taking the derivative of this and confirm that in fact you get that. Good. And then remember there's a constant. Now again, just like before, technically each one of these has its own little constant, and then you can add all those little constants together, say it's one big constant, but most of the time people just add a c at the end there. Good, so we can simplify this a little bit and say that this is equal to 1/2. The 2 and the 4 will reduce to 1/2. X to the 4th power minus 3/2 x to the 2nd power plus 4x plus some constant. Okay, so that's potentially our answer, but then just check. This is sort of what we thought, so let's check it. Check to make sure. The derivative with respect to x of 1/2 x to the 4th minus 3/2 x to the 2nd plus 4x plus some constant c. Okay, so this derivative will be 1/2 times 4 x to the 3rd minus 3/2 times 2 x to the 1st power plus 4 plus 0. And now 2 goes into 4 twice, and this 2 and this and this 2 cancel, and so we get exactly what we were expecting. This becomes 2x to the 3rd power minus 3x plus 4, which is exactly what we started with in the integrand. That matches with this. So that confirms for us that in fact we do have the right answer. Right, so this is our answer. So here this is our answer. Okay, so the nice thing about this section is that if you have time to do the checking, you can always confirm that you have the right answer. So that should be helpful on the test. If you think you have the answer, then just take a minute and check it and confirm that in fact the derivative of your answer really is equal to the original value given, the integrand. Okay, let's try another one. What about something like this? So the integral of 3 e to the x plus 4 over x. So again, because there's an addition symbol there, I know that one of our properties lets us separate this. So this is equivalent to the integral of 3 e to the x dx, don't forget to include the dx, plus the integral of 4 over x dx. So finding these two separate integrals, the same thing as, and adding them separately is the same thing as finding this. Okay, so one of our properties also lets us pull the 3 out. 3 integral of e to the x dx plus, and then we can also pull out that 4 integral of 1 over x dx. Okay, so these are two well-known integrals. So the answer to this one would be 3 times, and this is just e to the x, right? The derivative of e to the x equals to e to the x, plus 4 times, and then this is ln of, and we just have to be careful to include the absolute value of x. And of course, there's always plus c. Good. So again, you can check and confirm that the derivative of this, well, that's easy. That's going to be equal to that. And the derivative of this, well, that's easy. That's going to be 4 over x. So it seems to make sense that this is definitely our answer. Okay, let's take a look at a few more examples. So, find the integral of 5 divided by x to the power of 4. So we know from one of our properties that we can always pull that 5 out and say that this is 5 times the integral of 1 over x to the power of 4 dx. And we also know that we can rewrite that yet again as 5 times the integral of x to the minus 4 dx. And so now we can use the exact same property we've been using. So this is going to be equivalent to 5 times, and then x to the power of, remember we're looking for a function whose derivative equals to this. When we find derivatives, we're going to subtract 1 from the exponent. So when we find the antiderivatives, we got to add 1. This is going to be negative 4 plus 1. And when we figure out what that is, negative 4 plus 1, we know that that's going to go to negative 3. So negative 3 is what goes here. This becomes, oh, let me make some space actually. This becomes 1 over negative 4 plus 1. That, which again is just going to be negative 3 plus some constant. So this is 5 times 1 over negative 3 times x to the power of negative 3 plus some constant. Can you distribute? And we get that this is negative 5 thirds times x to the negative 3 power plus 5 times this constant from there. So let's change it a little bit. Let's say that this is c sub naught. And now 5 times c sub naught, well, that's just equal to some constant, right? So it doesn't matter. This is negative 5 thirds x to the negative 3 plus some constant. Okay, so let's check it. Let's make sure that it works. Okay, so now let's check it over here. Check to make sure that it works. The derivative with respect to x of negative 5 over 3x to the negative 3 plus c. Okay, so then the pattern for derivatives, this is going to be negative 5 over 3 times negative 3 x to the negative 3 minus 1 plus 0. We take the derivative. So this becomes, these 3's cancel. This 3 cancels with that, and so we end up with positive 5. Positive 5 x to the minus 4 plus 0, which gives you 5 over x to the 4th power. That's exactly what we were looking for over here. So that confirms for us that this is in fact the right answer. So we can leave it like this, or we can also rewrite it to be this. This is equal to negative 5 over 3x to the positive 3rd power plus some constant. So either one of those is fine as our answer. Okay, so now let's try this one. So before we dive into the answer, I'm just going to rewrite it a little bit. This is equivalent to the integral of 4 times t to the power of 2 divided by 3 dt. And so by one of our properties, I can pull that 4 out. This is 4 times the integral of t to the 2/3 power dt. And then just following the same pattern we've been using. Up to now, they've always been constants, 1, 2, 3, 4, 5, 6. They've been natural counting numbers. But there's nothing in the property that says you can't have a fraction. So we can just follow it in the same spirit. This is going to be 4 times, and this is going to be t to the power of 2/3 plus 1. And then this is going to be 1 divided by that same thing. So it's going to be 2/3. Let me make space. 2/3 plus 1. And this is 4 times. And then there's that whole plus constant thing. I'm just going to leave that alone and say it's plus some constant. Okay, so then simplifying this just a little bit, we get 4 times. Now 2/3 plus 1, we need a common denominator. So let's multiply that by 3/3. That gets us to 5/3. So this is going to be t to the power of 5/3, 1/5/3, plus some constant. And so this will be equal to 4 times 3/5 t to the 5/3 plus some constant. And then, well, we can just multiply that and get 12/5 t to the 5/3 plus some constant. Good. The original question came in this format, so we might want to simplify it a little bit more. And so we could rewrite this as 12/5 times, and then this is the cube root of t to the 5th power, which is the same thing as pulling out 1t and having t squared inside the root. Cube root of t squared plus some constant. Okay, so let's check it. Check, is it true that ddt of 12 divided by 5, t to the 5/3 plus c, is it true that that's going to give us exactly that? Okay, so following our rules of derivatives, this becomes 12/5 times, bring down the 5/3 times t to the 5/3 minus 1 plus 0. And now the 5's cancel, and 3 goes into 12 4 times, so that gets us that 4 that we wanted. And so this becomes 4 times t to the power of, and again we need a common denominator, which is a 3/3. So let's rewrite that as a 3/3, which gives me 5 minus 3 is 2/3. 2/3, which then can be rewritten as 4 times the cube root of t squared. Good. Okay, so it works. We've confirmed it, checks out, so we feel confident that this is our answer. So it can be either one, right? I'll just put an or and box them all up. All right, one more example. What if we had something like this? Ooh, that's ugly. And I know that when we're finding derivatives and we see an ugly fraction like this, right away we start thinking about the quotient rule, right? Low d high minus high d low over the denominator, squared we go. But remember, we're not finding derivatives. We're trying to go backwards. We're trying to find some function whose derivative equals this. That's pretty ugly. So just in general, if you run into the integral of an ugly fraction, sometimes that's pretty, there's going to be different techniques that we're going to have to employ to find the answer, and sometimes we might not be able to find the answer. Luckily, in this case, the way it's written, there is a fairly simple answer. Notice that we can very easily separate this one big fraction into the subtraction of two different fractions. So, using a little bit of algebra, we can just rewrite this as x to the power of 4 divided by x squared minus 2 over x to the power of 2. All of that is still being integrated. And now there is a subtraction sign, so we can separate them, and also these reduce. So this is equal to the integral of x squared dx minus, and then I'm going to go ahead and put that 2 out in front, the integral of 1 over x squared dx. Good. So this is equivalent to the integral of x squared dx minus 2 times the integral of x to the minus 2 dx. Now we're ready to find the antiderivative. This is going to be equal to x to the power of 2 plus 1, which is going to be 3. And there's going to be a 2 plus 1 out in front, minus 2 times, and then this is going to be equal to the power of negative 2 plus 1. So there will be a 1 over minus 2 plus 1 out in front, plus some constant. And now we just simplify this. This is going to be equal to 1/3 x to the power of 3 minus, and now negative 2 plus 1 is going to be negative 1. So this is going to be equal to 2 times 1 over negative 1 times x to the negative 1 power plus c. And so that will simplify as 1/3 x to the third power. The minus and the minus turn into a plus 2 times, and then x to the negative 1 power is 1 over x. Or we can just write 2 over x, just to make it extra nice. 2 over x plus c. Good. And so that's our answer. And we can come over here and do a little side work to check it, just to make sure. Check that in fact it's true. So is it true that the derivative with respect to x of the function 1/3 x to the third power plus 2 over x plus c is equal to that? Okay, so let's figure it out. The derivative of this is going to be 1/3 times 3 x to the second power plus the derivative of this is going to be equal to 2 times negative 1 x to the negative 2 power plus 0 plus 0. So now the 3 and the 1/3 reduce, giving me x to the second power minus 2x to the minus 2 power, which then becomes x squared minus 2 over x squared. And bringing these two together, I'm going to multiply the numerator and denominator of this function by an x squared over an x squared, which gives me x to the fourth power minus 2 divided by x squared. Exactly what we were expecting. So it confirms that this really is, in fact, our correct answer. Okay, example 4, applications of a particular antiderivative. So find the equation of the curve that passes through the point 3, 5 if the slope of the curve is given by dy dx equals to 2x at any point x. Okay, so they've given us this. They've given us dy dx, so we're looking for a function. We want a function y such that the derivative with respect to x, d dx of the y, otherwise known as dy dx, is equal to 2x. So in function notation, we can also say we're looking for f of x, or we want to find some f of x such that f prime of x equals to 2x. Okay, so we want a function whose derivative equals to this. Okay, so we want the integral of 2x dx. that'll be a function whose derivative is equal to 2x. Okay, so that means that this is going to be equal to x squared. Okay. A function whose derivative is equal to this one, plus some constant. Okay, so this describes a whole family of functions, but in particular, we also want to find the function, the answer, that satisfies this. It's got to go through the point 3, 5, which means that the input, when the input is 3, the output is 5. Or in the x and y notation, when the x is a 3, the y is a 5. So we have this equation here. And so we're going to use these boundary points there. We're going to let y equal to 5 and x equal to 3. And that'll help us find our c. So this is 5 equals to 9 plus c. So therefore, 5 minus 9 equals to c. Or we get that c equals to minus 4. And finally, we can get to our answer then. So y equals to x squared minus 4 is the equation that satisfies the conditions given. So the derivative of this is going to be equal to 2x, right? So find the equation of the curve that passes through this point if the given slope is equal to if the slope of the curve is given by dy dx equals to 2x for any point. Okay, so just to check it, check y prime equals to 2x, just like we expected. And also note that if we plug in the value x equals to 3, we get that y equals to 3 squared minus 4, which means that y equals to 5. So the ordered pair 3, 5 is on the graph. Okay, let's take a look at it, right? It's just a parabola. So it's very similar to the one we saw earlier. Let's get rid of all of these guys. This is so this is the particular one that we're looking at, and we had that the point 3, 5 is a point on my function. Okay, so the question was to find a function, find a curve that satisfies these two conditions. Its derivative must be equal to 2x, and that it must go through the point 3, 5. And so we found it right here. So this is the function that satisfies that. This is the equation y equals to x squared minus 4, right? It's just a parabola that's been shifted down and has a vertex down here at the point 0, negative 4. Okay, let's try one last one. Example 5. If the marginal cost of producing X units of a commodity is given by C prime of X equals to 0.3 X squared plus 2X, find, with fixed cost of 3,000, find the cost function C of X and the cost of producing 30 units. Okay, so they want you to find C of X given that the derivative of C of X is equal to this. So we're interested in the following. C of X C of X is equal to the integral of C prime of X dx. Right? Note that, well, okay, let me take a step here, okay? We can also rewrite this as the integral of the derivative of c of x dx. Remember, these two operations undo each other. So that's kind of like writing the square root of something squared, if x is positive, because if it's negative, then we have an issue. But if x is positive, then these two kind of undo each other. Or when we're working with, say, e to the power of ln of 3, these two operations just lead to a 3. Okay, so this is the same thing as this, dx, and well, this is what they gave us. So this is the integral of 0.3 x squared plus 2x dx, like that. And so we know that this is going to be the integral 0.3 x squared dx plus the integral of 2x dx. And so following our pattern, this is just going to be equal to 0.3 times, and this is going to be x to the power of 3, 1 over 3. Right? The derivative of this, we bring down the 3, cancels with this one, subtract 1, we get to that. Plus, and then this one is going to be x to the power of 2. Bring down the 2, we get that exactly right there. Plus some constant c. Good. We can simplify this a little bit. 0.3 is the same thing as 3 divided by 10. That's 0.3 times 1/3 x to the third plus x squared plus c. And so the 3's cancel there. And so we have just 1/10 x to the third power plus x squared plus c. Okay, so we're almost there, except that we'd like to figure out what that constant is. And luckily, they gave us some information to be able to figure that out. So coming back up here, notice that the problem says that there is a fixed cost with a fixed cost of $3,000. A fixed cost means that when you produce 0 units, you still have to pay $3,000, right? It's like paying the rent. It doesn't matter whether your factory produces anything or not, you still have to pay the rent. So this fixed cost equals 3,000 lets us know that when x equals to 0, then the output of our function must be equal to 3,000. Oh. Not the function. Our cost is still equal to 3,000. So we have this c of x equals to 1/10 x to the third power plus x squared plus c. And so now, putting a 0 there gets me 1/10 0 to the third power plus 0 to the second power plus c. And so these are just going to be 0, and we know that 3,000 better be the output when we put in zeros. So this must be true. 1/10 times 0 plus 0 plus c, therefore c must be the 3,000. Okay, so now we have our complete equation. This is 1/10 x to the third power plus x to the second power plus 3,000. And finally, we can get to the last part here. They asked us to figure out what's the cost of producing 30 units. So now all we have to do is evaluate this at 30. Oops. 1/10 cubed plus blank squared plus 3,000. And so we evaluate it at 30 there, 30 there, 30 there. So this is going to be 1/10 times 30, that's going to be equal to 900 times 30, that's going to be 27,000 plus 900 plus 3,000. 27,000 divided by 10 is going to be 2,700. So this is going to be 2,700 plus 900 plus 3,000, which then gives me 6,600. So C of 30 equals to 6,600. Okay, so the cost to produce 30 units will be 6,600. Find the cost function C of x. Okay, so the cost function C of x, including the constant, is this one. So this is a preliminary answer. It's not the answer to this question. So here is one of our answers. It's this one. Here is the cost function, including its constant. And now the second answer is this one, and we might want to have a nice little sentence. The cost to produce 30 units is 6,600. Okay, so that should be enough to get started on your homework. As usual, stop by my office hour if you have any questions.